right, getting into this chapter 16. Woo! Finishing up here part 2 of our chapter 16, actually. So let's get into it. So we're going to start by talking about Lewis acid and Lewis bases. So this is another way that we can view the exchange of electrons and atoms in chemical reactions. And this is a little bit different than the models we've been talking about before, mostly the Bronsted and the Lowry models, right? Where acid is a proton donor and a base is a proton acceptor, or a base produces hydroxide and acid produces H+. So what we're going to see here in this model with the Lewis acid base model, a Lewis acid accepts a pair of electrons, and a Lewis base donates a pair of electrons. Okay, so for example, if we look at our reaction here with ammonia, of course we've described this as the Bronsted model, right, where the base accepts a proton, but now you can see this looks a little bit like it's the opposite here. And in fact, this is a more correct model for what's actually going on in the chemistry. So you can see this NH3, if we were to draw its Lewis structure, we would find that it has that lone pair right here, okay? And we know that the NH3 becomes NH4 plus ammonium. It's making a nitrogen-hydrogen bond, and it makes that bond by donating this pair of electrons to the hydrogen on water. So the ammonia is acting as a Lewis base because it's donating electrons. And then the water now is acting as a Lewis acid because it's accepting those electrons. And now we still have to conserve the octet rule. So I'm going to write that down. Octet rule must hold, okay? So when this electron pair gets donated to these hydrogens, we're now violating the octet rule. So the electrons in this bond now get pushed over to the central atom, and then now that appears as a new lone pair. So here we can see bond breaks and new lone pair forms. And then, of course, we've also made a new chemical bond from those donated electrons. Okay? So let's see another example. So here now we're looking at calcium oxide and sulfur dioxide. Okay? And in this case, we can see the oxide, it has a large abundance of lone pairs. It's got a lot of lone pairs to give. Okay? So it's donating its lone pair to the central sulfur atom. Okay? So we can say this is the Lewis base. I'll say Lb. And then because this SO2 is accepting the electrons, it's the Lewis acid, the La. And then once again, because we have to now, in this case, it's not so much the octet rule, because we remember sulfur can violate the octet rule. So the octet rule must be conserved. But also when the octet rule is being violated, that also must be conserved. So we can see 1, 2, 3, 4, 5 electron lone pairs around the sulfur, right? So when this bond comes in, that's a 6th pair. So what happens is this double bond breaks, and now we make the sulfur trioxide that still has the 1, 2, 3, 4, 5 electron pairs. Okay. So another example, again, with ammonia, and hopefully what you can tell right now, there's certain molecules that are just always going to act as Lewis bases because they have lone pairs to give. Ammonia is a good example of this. I'm going to say almost always a Lewis base because it has those lone pairs to give. Okay. And then now you can see it makes a lovely chemical bond with this boron trifluoride. And boron is a really interesting molecule in that it's happy with only 3 bonds, but it's also happy with 4 bonds. So there's no more electron rearrangement here. It just makes the new chemical bond. Okay, so let's do an example here. Example 16.6, which species is a Lewis acid and which species is a Lewis base. So there's 2 different reactions, so we're going to do each reaction one at a time. So we'll say reaction number 1, reaction number 2. So if you want to pause the video and work through this beside me, go for it. Or you can watch me go ahead and solve through this. So the first thing that I'm going to do is get the Lewis structures. So let's do this reaction number 1. Okay, and when I see this aluminum trichloride, hopefully I can see that this one is a pretty straightforward. There's going to be 3 chlorines surrounding the aluminum, and we remember that I've got to make enough lone pairs to satisfy the octet rule. So that's 2, 4, 6, 8 around this chlorine. So now I've got 2 in the bond, 4, 6, 8, and 2, 4, 6, 8. And there is our Lewis structure for the aluminum trichloride. And then now, of course, we have a chloride, just plain old chloride. And we remember that when we have the basic monoatomic anions, they're just going to fill out all around. And we remember that chlorine only had 7 electrons, right? 1, 2, 3, 4, 5, 6, 7. But because of the negative charge, that makes an 8th electron. So we've got 8 electrons surrounding there. And so now I'm going to also write the Lewis structure for the final product. And you can see here that that's just now an aluminum with 4 chlorines. And I think if you get the Lewis structures for all the reactants and all the products, that's going to help you see which way the chemistry goes. Okay? So you can see what happens is we're creating a bond from aluminum to chlorine, right? And because chlorine has all of these electrons to give, we recognize that chlorine has to be the Lewis base, so I'll say Lb, and aluminum trichloride has to be the Lewis acid because that's what's making that new chemical bond. Okay? Let's look at the second reaction. So once again, we're going to get those Lewis structures. Hopefully you remember the Lewis structure of carbon dioxide looks something like this. It's got the double bond and the 2 lone pairs surrounding. And then now when I already showed you the Lewis structure for calcium oxide, but as a reminder, when we write the Lewis structure for those ionic compounds, the cation is always deficient of electrons, so it's just a calcium 2+. And then now my oxygen, we know has 6, 1, 2, 3, 4, 5, 6, but because it's the 2-, that 2- is going to add 2 extra electrons, okay? And then now, if we go and do the Lewis structure of the final product, that's also going to help us see what this thing should look like. And now we remember that carbonate is a polyatomic ion, and it does have a resonance structure, but we don't necessarily need to draw the resonance structure to see what's going on here. Okay, so this is what carbonate looks like. And now, once again, if we inspect our structures here, we can see we're making a new chemical bond. And specifically here, we're making a new single bonded oxygen. So what's going to happen is the oxygen lone pairs are going to attack the carbon, and that makes the calcium oxide the Lewis base and the carbon dioxide the Lewis acid. So this arrow right here represents a new chemical bond to oxygen. But now, because we're going to violate the octet rule, one of these bonds has to get pushed over to the atom to become a lone pair. And it doesn't matter which one we draw, so I'm just going to draw this one. Okay? So now what these arrows represent here are, once again, a new chemical bond being formed. So that violates the octet rule for carbon. So then now one of these bonds gets pushed over to making lone pairs. And there we have it. We can see we're left with the double bonded oxygen with 2 lone pairs, which is right there. We've got a new single bonded oxygen with 3 lone pairs, 2, 4, 6, because remember, this lone pair became the bond. So there it is, single bond with 2,4,6. And then now we've made another new single bond with oxygen with one single bond and 2, 4, and then the bond becomes 6 electrons, 3 lone pairs. And there it is, 2, 4, 6. Okay, lovely, folks. So if you need some more review on Lewis structures, I would encourage you to do so. Just the simple ones will suffice, just so you can put together these structures and really see what's making the new chemical bonds.